Hello and welcome back to my channel. Today we'll be seeing something different, revisiting test of divisibility by prime, part 1. So we start with a simple but awkward question that whether this 8-digit number divisible by 67. It is awkward, but if you have a calculator or even a cell phone, you can easily answer this question. But is it not quite intriguing that if there is a thumb rule, whether you can test the divisibility of this number by 67? In fact, divisibility tests have always fascinated people, and even in class 4 textbook of mathematics, there are listed a few thumb rules by prime number 2, 3, 5 and 11 and also 9, which is not a prime of course. And moreover, most modern number theory textbooks, they present this list and also explain why do they work. Okay. So what we will see that divisibility test S by P. P is the prime. Okay. The thumb rule that are available. First one, if the last digit of S is divisible by 2 or 5, then the number S itself is divisible by 2 or 5. And rule number 2, if the sum of all the digits in S is divisible by 3 or 9, then the number itself is divisible by 3 or 9. So you all know these two thumb rules. What we are basically doing, let us see. So suppose that S is the given number, the digits are A0 to AN, so it's a n plus 1 digits number. And what we are doing, we are trying to extract, okay, so an example 1, 2, 3, 5, if the number 1235, the digits are like this. So 5 is A0, 3 is A1 and so on. So what we are basically doing in these rules, from the given bigger number S, we try to extract a much smaller number C. Of course, C can be expressed in terms of the digits itself of the given number. And then the rule demands that if that smaller number is divisible by P, which we can manage very easily, we can check it, then the rule demands that S itself is divisible by P. So if C is divisible by P, then S is divisible by P, where you have extracted C from S by some special rule. Well, in that spirit, so if we look back again, test 1, what is C in case of P equal to 2? The rule says that the last digit. That means C is nothing but the last digit itself, A0. Okay. Of course, it indicates if the number S ends with 0 or with any even digit 2, 4, 6, 8, even digit. Okay. So in case of 5, similarly, again C is nothing but the last digit A0 only. So if A0 is divisible by 5, then S is also. Of course, it indicates a number that ends with either 0 or 5. Fine. Now the rule 2 is slightly different. It tells about the sum of the all digits in S if it is divisible. That means here C is nothing but sum of the digits of the given number S. That means sum over I equal to 0 to n A I. So for example, 369, you just add 3 plus 6 plus 9, 18, and 18 is divisible by 3, so 369 is divisible by 3. The rule goes like that. Well, for 11, it's slightly different, and in this case, C is nothing but a sum like this, but the plus minus coming alternately. So A0 plus minus A1 plus A2 minus A3 and so on. That means the A0, A2, A4 are added, and from here it subtracted the sum of the digits A1, A3, A5 and so on. So look at the example. So 154 is the number, then you add 4, the last digit A0, then A2 minus A1. So 4 plus 5 minus 5 is 0, right? And it is divisible by 11. So 154 is divisible by 11. So here is a summary. Test 1, test 2 and test 3 we can call. In the first case it is last digit for 2 and 5. And the second test it is the sum of all the digits for 3 equal to p equal to 3 and 9. And test 3 we call C is nothing but the alternate plus minus sum of the all digits for p equal to 11. Okay. And what about p equal to 7? As we see in class 4 textbooks, there is no thumb rule for p equal to 7, but we will present it. But you have to wait for the next video for that. Okay. Now we have a few questions, and what we'll see that this criteria, this thumb rule, where do they come from? Or in other words, what is the rationale behind the thumb rule? The second question, are they all really different, or having a common single, maybe more than one, generalized versions, right? And what about other primes? Are these criteria enough for any p in general? And we will see the tests, that is test 1, 2 and 3, however different they look, are actually not very different from each other. The second thing we will see that we will present a generalized common strategy, we will call it strategy 1, and then we will see that this strategy 1, it leads to all the 3 popular tests narrated so far. Okay. And moreover, the strategy 1 is applicable for any p in general. But what is that general strategy? Okay. So suppose we start with the given number s like this, and we want to extract c from s. And how do we do that? So our proposal is, we claim that strategy works with examples. Of course, for justification you have to wait for the next video, and please wait. But today we will be seeing that how the strategy 1 leads to all the popular tests. And what is that strategy 1? Well, here it goes. So strategy 1, and we propose that C that you want to extract from S in terms of the digits AI is nothing but sum of mi AI. That means the digits themselves, they are multiplied by the corresponding multiplier mi, and then sum. Okay. So that is your C. Now, what is that mi? Mi is nothing but remainder of 10 minus p to the power I by p. So p is the prime number by which you are dividing the number s, and 10 minus p to the power I, that is your mi, where I goes from 0 to n. Okay. So mi is the value of the remainder when 10 minus p to the power I is divided by p. So that we can easily calculate, as we will see for p equal to 2 first, test 1. So p is 2, so 10 minus p is 8. So mi is 8 to the power I divided by 2, its remainder, and you can easily check that mi is 0 for all I except I equal to 0, and for that I equal to 0, m0 is 1, because 8 to the power 0 is 1, so 1 by 2 remainder is 1. Otherwise 8 to the power 1 or 8 to the power 2 or 8 to the power 3 up to 8 to the power n, all are divisible by 2, and hence remainder is 0. Well, so what happens that in our C, mi ai for I equal to 1 to n other than 0, all are 0. So this part vanishes except I is 1, and that mi is 1, so 1 into a0, that means simply a0, the last digit in S as usually presented in the texts. Okay. Now for 5, very similar, but this time p is 5, so 10 minus p is 5, so remainder 5 to the power I by 5, that is mi, And again you will see that mi is 0 for all I except I equals to 0. In that case, m0 is 1. Why? Because 5 to the power 0 by 5. So 1 by 5, remainder is 1. But otherwise 5 to the power 1, 5 to the power 2, 5 to the power 3 and 5 to the power n all are divisible by 5. So remainder is 0. So again we see that 1 to n, this part vanishes and the only one part exists, 1 into a0, or m0 is 1 and a0. So that is a0, the last digit in s, as again usually presented in texts. Now we will see for p equals to 3, test 2. So again you quickly see that p is 3, so 10 minus 3 is 7. So mi is simply remainder of 7 to the power I by p. P is 3. 7 to the power 0 by 3, remainder is 1. 7 to the power 1 by 3, again remainder is 1. Remainder 7 to the power 2 by 3, so 49 by 3, that means again remainder is 1. And you can easily check that actually mi is 1 for any I. That means C is mi ai and all mi are 1, so it is simply 1 into ai, that means sum of ai. So it is sum of all the digits in S as usually presented in texts. Now we will see p equal to 9, though it is not a prime, but again it is applicable. 10 minus p, so p is 9, so 10 minus p is 1. So mi is 1 to the power I by 9. Now 1 to the power anything is, you see 1, so 1 by 9, remainder is 1. That means all mi again are 1, and that means C equal to nothing but sum of 1 into ai, that means sum of all the digits in S, as again usually presented in text. Now we will see for p equal to 11 and slightly different. So again p is, okay, 10 minus p is 10 minus 11, so minus 1. So mi is nothing but remainder of minus 1 to the power I by 11. So of course you can understand that minus 1 to the power I, so if it is 0 then plus 1, if it is 1 then it is minus 1, and so on. So you can easily check that it comes alternately 1 minus 1. m2 is again minus 1 to the power 2, so that is 1, so 1 by 11, remainder is 1. But minus 1 to the power 3 is minus 1 by 11, so remainder is minus 1. Okay, so it goes like 1 minus 1, 1 minus 1, 1 minus 1, right? And that is the demand of the rule. Like for 3-digit number, a0 plus a2 minus a1. For 4-digit number, for 5-digit number, so you see that's 4 plus 3 plus 2 alternately, minus 7 plus 2, 7 plus 2, minus 7 minus 2. So again you can easily check that it gives you 0, and 0 is divisible by, of course, 11. So the number is also divisible by 11. Well, so what we have seen so far, the popular divisibility tests for p equal to 2, 5, 3 and 11 and of course 9 are narrated with examples, and we have presented a generalized strategy 1, and we have shown that all the above 3 tests arise from the same generalized strategy 1. But still we have some unanswered questions. What are those? The popular divisibility tests for p equal to 7 that we have not seen in this video with examples, and we have not applied strategy 1 either for test 4, you can call, that is for p equal to 7. And more importantly, the strategy 1 that is presented here, we have not explained why or how this strategy works, and whether strategy 1 can be applied for a few more p or any p in general. So all this would be coming in the next video, revisiting test of divisibility by prime, part 2. Until then, thanks for watching. Please come back for the part 2 to get all the unanswered questions answers. Thank you very much.